Uh, Today we will again study perturbation methods by adopting a different procedure. This is something different from the previous one because in previous one we find out the change in perturbation energy. Here we will also get perturbation, but in term of first order, second order, third order energy change, a correction, energy correction. Since second and third order energy corrections are still smaller in comparison to first order energy correction, that's why we will omit second and third order energy corrections, and only we will discuss to first order energy correction. As in previous lecture, we have discussed the Schrodinger wave equation for a perturbed system H psi equal to E psi. Schrodinger wave equation H psi equal to E psi. A system can have an energy state, so it can be written as H psi n equal to E n psi n. This is for Schrodinger wave equation for perturbed system. For perturbed system. If on this system, if on the how it has been obtained, if on an unperturbed system we applied a force like electric field, electrostatic potential or magnetic field, then we get perturbed system from an unperturbed system. Suppose the relation for unperturbed system is H naught psi naught equal to E naught psi naught. For an energy state, it can be written H naught psi n equal to E naught psi n naught. This is the Schrodinger wave equation for a Hamiltonian of unperturbed system. This is unperturbed. Schrodinger wave equation for unperturbed system. Suppose our system is for hydrogen atom. As the amount of electrostatic potential increased, perturbation is also increased. Suppose system is perturbed, or that can be also termed as disturbed, its Hamiltonian is changed. Now the changed Hamiltonian may be written as H equal to H naught, this is Hamiltonian for unperturbed system, plus perturbation. This term is we call perturbation. This is lambda is parameter. As we increase the value of lambda, perturbation will also be increased. Here the term used in above relation is used. Lambda is parameter that may be electric field, electrostatic potential, magnetic field, etc. H naught is unperturbed Hamiltonian. Lambda H is correction or perturbation. H is total Hamiltonian. And the amount of perturbation is very, very less in comparison to unperturbed Hamiltonian. Here we will use a mathematical tool known as Taylor series, which is expressed as, since our function is the variable of lambda, f lambda equal to f naught lambda power 0, lambda power 1, f prime, f dash plus lambda square upon factorial 2 f double prime. First prime, second prime is called first derivative of function, and second derivative of function lambda cube upon factorial 3 f triple prime plus, and so on. Here it has been written what f prime, f double prime indicate: first derivative of function, second derivative of function, and third, and so on. From above Taylor series, we can write similar expression for wave function and energy term. Here we can write for wave function psi n lambda psi n 0 plus lambda power 1 psi n prime plus lambda square upon factorial 2 psi n double prime plus lambda cube upon factorial 3 psi n triple prime, and so on. And for energy, similarly, we can write this expression En 0 lambda power 1 plus En prime lambda square upon factorial 2 En double prime, and so on. Where psi n 0, En 0 is 0 order term, lambda power 1 psi n prime, or psi n here we can use psi n 1, psi n 1, since in place of prime we use term 1 also, which indicate first order energy correction or wave function correction, second order wave function and energy correction. So further we will use in place of double prime digit 2, lambda square psi n 2 psi n double prime and lambda square upon factorial 2 En power double prime, second order wave function. This is second order wave function, and this is second order energy term, energy correction, and this for third order energy correction and wave function. Putting the value of these equation 2, 3 and 4 in equation 1. Here 2, 3 and 4 into equation 1 for an energy state for perturbed system. What will we get? Just simply putting these values into equation 1, we can write h naught plus lambda h one, which is perturbation, psi n naught plus lambda 1 psi n 1, it's lambda square factorial to psi n 2. This is psi n 1 psi n 2, it comes in place of psi n prime psi n double prime, equal to En naught lambda power 1 En 1 lambda square upon factorial 2 En 2 lambda cube upon factorial 3 En 3, which was in previous case is in expansion we have write power triple prime. Here we are using En 3 into psi n 0 plus lambda power 1 psi n 1 plus lambda square upon factorial 2 psi n 2. Now multiplying this term into this whole bracket and this whole bracket term into this, and so on. Here also third term can be written, which indicate third energy and wave function, energy correction and wave function. This is 3. Yeah, third term can also be written plus lambda cube upon factorial 3 psi n 3, and so on. Upon multiplication, we'll get H naught psi n naught. First, this will multiply into this. Second, this will multiply into this. This will multiply into this. In next round, this term will multiplied by this whole 3 term which has been given in this bracket. This lambda h1 multiplied by psi n naught, lambda h1 multiplied by lambda 1 psi n 1. Again, this will multiply into this. We will get this result. Again, equal. In right hand side of this equal sign, we will multiply this whole term into this, and we will get this result. You very easily you can do all these things. If there will be any problem, we will discuss in class. If coefficients are same, we can equate them. Here coefficient of lambda, coefficient means coefficient of lambda, then we can equate them in equation 5. This is equation 5, and this is power series of lambda. Here power of lambda is 0. This is power of lambda. In this term, power of lambda is 0. Here power of lambda 1, power of lambda 2, and this will further increase power of lambda 3, which comes in further in series. But here only second power of lambda has been given, but third will also come if we further expand this series. So we can equate the power of lambda on both sides of equal sign. Here in this series, power of lambda, when we equate the power of 0 power of lambda, the coefficient of 0 power of lambda, we obtained H naught psi n naught equal to E n naught psi n naught. When we equate first power of lambda, coefficient of first power of lambda, what we get? H naught psi n 1 plus H1 psi n naught equal to E n naught psi n 1 plus E n 1 psi n naught. This is equation 7. And if we equate the coefficient of lambda power 2, second power of lambda, what we get? H naught psi n 2 plus H1 psi n 1 equal to E n naught psi n 2 plus E n 1 psi n 1 plus E n 2 psi n 2. This is equation 8. Here, from equation 6, what we get? H naught psi n naught equal to E n naught psi n naught. What this is indicates? This is the Schrodinger wave equation for unperturbed system, which we already know, because for hydrogen atom we already for unperturbed system we have already proved exact, we have already obtained exact solution. So to whose solution, exact solution is already known to us, so this is no meaning for us at the moment. Here we want to try to get the energy correction, first order energy correction by the applying perturbation, which is caused by electrostatic potential. Here in present case, in which we have used electrostatic potential. Now comes on equation 7. In equation 7, energy of first order energy correction, because it's the first power of lambda, so we are termed this thing as a first order energy correction. Now in equation 7, multiplying by psi n naught star on both sides of equation 7, what we will get? Psi n naught star h naught psi n1 plus psi n naught star h1 psi n naught equal to psi n naught star en naught psi n1 plus psi n naught star en1 psi n naught. This is equation 9. Integrating on both sides, what we will get? Integration psi n naught star h naught psi n1 d tau plus psi n naught. This whole term can be written as above by applying integration sign with respect to d tau, which is volume integral. You already know it in 3D system. Here, since h naught psi n1 equal to en naught psi n1, since s psi equal to e psi, then this whole term psi n naught h naught psi n1 and this will be cancelled out to each other. This can also be understood by Hermitian property of the operator. All the quantum, as we know, all the quantum mechanical operator are Hermitian in nature. So this Hermitian property has been written here. If our wave function is psi I star a psi j, then it can be written as, we place this, if this is first, this is second, this is third, this interchange its place, then we can write, and we change its place and take the complex conjugate of whole term, all term, and it becomes psi j star a psi I, and whole term complex conjugate of whole term, then it becomes complex of this complex, such as minus into minus equal to plus, then complex of complex become real quantity. Then it can be written psi j a, this is real. If it, this operator is real, then it will also real, but here complex sign has been written here, and psi a star. Same thing has been applied in the, here we can direct cancel out each other, and you can understand from this. Which can be written psi n1 h naught star psi n naught star plus psi n naught star h1 psi n naught d tau. This from here, this has been written. Due to Hermitian operator property, two terms above equation have been cancelled out, which I have earlier discussed here. From here, which has been cancelled out. How it cancelled out? From this step to this step, it has been try to solve how these two terms have been cancelling out to each other. After cancellation, what terms remains? En1. This term, because here only En1 term is remaining, since for normalized wave function we know psi n naught into psi n naught star d tau equal to 1. Hence this comes to 1, since wave function is now normalized. So here En1 into 1, that means En1, and this equal to psi n naught h1 psi n naught star d tau. This is the derivation for first order energy correction. Multiplying by lambda, the parameter which has been used for perturbation, it can be written lambda en1 psi n naught plus lambda h1 psi n naught star d tau. This is the first order energy correction by applying the electrostatic potential as perturbation parameter. Here En1 is the first order energy correction, psi n naught is unperturbed wave function, and psi n naught star the complex conjugate of unperturbed wave function. H1 is the perturbed Hamiltonian. From here we can find out first order energy correction. That's all for first order energy correction.